Bismillahirrahmanirrahim. I am Dr. Syed Azhar. Today we will discuss linearly independent vectors and linearly dependent vectors. Before starting the definition, for example, we have two vectors. Say u1 is 1 1, that is I plus j, and u2 is 2 2, that is 2i plus 2j. In xy plane, the graph of these two vectors will be just like this. Look at the graph of these two vectors. Clearly, these two vectors lie on the same straight line. That's why these two vectors are linearly dependent, because this is one of the conditions of linearly dependent vectors. In case of two vectors u1 and u2, it's quite easy to deal them, means to check them whether these are linearly dependent or independent. But if we increase the number of vectors, then it's quite laborious. So this definition gives us a tool to check whether the given number of vectors are linearly dependent or independent. Before this, in linear combination, we have x1 u1 plus x2 u2 plus x3 u3 up to xm um is equal to some specific vector. We said that this specific vector is a linear combination of u1, u2, u3 up to um vectors if there exist these scalars x1, x2, x3 up to xm. If this specific vector becomes a zero vector, then from this equation we get x1 u1 plus x2 u2 plus x3 u3 up to xm um is equal to zero vector. So in case of linear combination, from this equation we obtained a non-homogeneous system of straight lines, and in this case when the specific vector u becomes zero vector, then from this equation we obtain a system of homogeneous straight lines. And to check whether the vectors are independent or dependent, we have to deal with this equation. So in definition of linearly dependent or independent vectors, these vectors u1, u2 up to um will be linearly dependent if from this equation we obtained x1, x2 up to xm such that not all of them are zeros. If all of them become zero, then we will say that the given vectors u1, u2 up to um are linearly independent. Means in both cases, for linearly independent or for linearly dependent vectors, we have to deal with this equation and we have to find x1, x2 up to xm. If x1, x2 up to xm all are zeros, then we will say that the vectors are linearly independent. If not all of them are zeros, then we will say that the vectors are linearly dependent. In this example, we have to check whether these three given vectors u1, u2 and u3 are linearly independent or dependent. So for this purpose we will use this equation x1 u1 plus x2 u2 plus x3 u3 equals 0. Now put these three vectors, we get x1 into 1 2 3 plus x2 into 2 5 7 plus x3 into u3 is basically 1 3 5. And since in this equation on the right side we have 0, here 0 means 0 vector. Now multiply x1 with 1 2 3, x2 with 2 5 7 and x3 with 1 3 5, and after that add these columns. We get x1 plus 2x2 plus x3, 2x1 plus 5x2 plus 3x3, 3x1 plus 7x2 plus 5x3. From this equation we will get x1 plus 2x2 plus x3 equals 0. First equation 2x1 plus 5x2 plus 3x3 equals 0. Second equation 3x1 plus 7x2 plus 5x3 equals 0. Third equation. Now we have to solve this homogeneous system to find the values of x1, x2 and x3. For this purpose we have to write its augmented matrix. So its augmented matrix is 1, 2, 3 is its first column, 2, 5, 7 is the second column, 1, 3, 5 is its third column. Now, to transform this matrix in its echelon form, here this entry is the pivot entry, and echelon form, the entries below the pivot entry must be 0. So we have to eliminate 2 and 3 from this system. So for that purpose we have to use R2 minus 2R1 and R3 minus 3R1 row operations to eliminate 2 and 3 respectively. So first use the first operation, which is R2 minus 2R1. So 2 times R1 gives us 2, and subtract that 2 from this 2, we will get 2 minus 2 equals 0. 2 times R2 gives us 4, and subtract that 4 from 5, we will get 5 minus 4 equals 1. 2 times R1 gives us 2, and 3 minus 2 gives us minus 1. Now use the second operation, which is 3 minus 3 times R1. So 3 ones are 3, and subtract that 3 from this 3, we will get 3 minus 3 equals 0. 3 twos are 6, and subtract that 6 from 7, we will get 7 minus 6 equals 1. 3 ones are 3, and subtract that 3 from this 5 gives us 5 minus 3 equals 2. Now in this matrix, these are the pivot entries. Now we have to eliminate this entry 1. So for that purpose, we have to subtract second row from third row. So R3 minus R2 is our third operation. The first row will remain same, the second row will remain same. Now subtract this 0 from this, we will get 0. Subtract 1 from this one, we will get 0. Subtract this minus 1 from 2, we will get 2 plus 1, which is 3. Now clearly look at this matrix. Here we have 3 pivot entries associated with C1, C2 and C3. This shows that all the 3 variables are basic variables. So in case of basic variables, we know that we will get a unique solution. And in this case, since this one is the coefficient of x1, this one is the coefficient of x2, and this one is the coefficient of x3, and on the right side we have zeros. So this will give us 3x3 equals 0, means x3 equals 0. From the second row we will get x2 minus x3 equals 0. Put this value of x3 in this equation, we will get x2 equals 0. If from first row we will get x1 plus 2x2 plus x3 equals 0. Use these two values in this equation, we will get x1 equals 0. Since all the values of scalars are zeros, this shows that these 3 vectors u1, u2 and u3 are linearly independent. In this example, also we have to check whether these 3 given vectors are linearly independent or dependent. So similarly, we have to use this equation x1 u1 plus x2 u2 plus x3 u3 equals 0. Put the values of u1, u2 and u3 in this equation. After that, multiply x1 with 1, 1, 0, x2 with 1, 3, 2, x3 with 4, 9, 5. And on the right side we have 0 vector. Multiply x1, x2 and x3, and after that add these matrices, we will get x1 plus x2 plus 4x3 is equal to 0, x1 plus 3x2 plus 9x3 equals 0, and from the last row we obtained 2x2 plus 5x3 equals 0. Clearly this system is a homogeneous system, and to solve this one we have to write this system in its augmented matrix form. And its augmented matrix form is, if you write A, B are coefficient matrix A, both are same, because in homogeneous system on the right side we have zeros, so augmented matrix can also be written as a coefficient matrix A. Its first column will be 1, 1, 0, second column will be 1, 3, 2, and third column will be 4, 9, 5. Now this one is our pivot entry, so we have to eliminate 1. So for that purpose, just subtract first row from second row. We will get 1 minus this one, 0, 3 minus 1, 2, 9 minus 4, 5. The first row and third row will remain same, because in the third row here we have 0, so the third row will remain same. Now in this matrix, these are the pivot entries, so we have to eliminate 2 here. So for that purpose, just subtract second row from third row. First row will remain same, second row will remain same. Subtract second row from third. So 0 minus 0, 0, 2 minus 2, 0, 5 minus 5, 0. Clearly, these are the pivot entries associated with first column and second column. So this shows that x1 and x2 are the basic variable, while the remaining variable x3 is a free variable. So from the second row, we will get 2x2 plus 5x3 equals 0. Shift 5x3 on the other side, we will get 2x2 equals minus 5x3. Divide both sides by 2, we will get x2 is equal to minus 2.5x3. From the first row, we will get x1 plus x2 plus 4x3 equals 0. Put x2 equals minus 2.5x3 and add with 4x3. We will get 1.5x3. Now shift that 1.5x3 on the right side, we will get x1 is equal to minus 1.5x3. This shows that u1, u2 and u3 are linearly dependent, because for each value of x3 you will get new solution. So this shows that this solution is not a unique solution, because for each value of x3 you will get a solution. From the examples and the definition of linearly independent and dependent vectors, we obtained some main points. Number first, say we have vectors u1 up to um, and one of these vectors is a zero vector. Then all these vectors from u1 to up to um will be linearly dependent. Why? Say u1 is our zero vector. Then we can write 1 dot u1 plus 0 dot u2 plus 0 dot u3 up to 0 dot um is equal to 0. Why? All these gives us 0, and since u1 is a zero vector, so if we multiply 1 with 0, from this we also obtain a 0. So this shows that these scalars are 0, but x1 is not 0, and for linearly independent vectors all these scalars must be 0. So that's why if there exists a zero vector in the collection of vectors, then that collection will not be independent. That collection will be linearly dependent. The second one is a non-zero vector u by itself is linearly independent. For example, we have collection consists of only a single vector, say u. So this vector by itself is a linearly independent vector. In the third, two vectors are linearly dependent if and only if they are the multiple of each other. In the start, in the definition, we actually used two vectors. u1 was 1 1 and u2 was 2 2, and we discussed there that these two vectors are linearly dependent. Look at these two vectors. From these two vectors we can write u2 is equal to 2 times u1 and u1 is equal to 1 over 2 times u2. So u1 and u2 were the dependent, and from that we can write u2 is equal to 2 times u1, u1 is equal to 1 over 2 times u2, means one vector is the scalar multiple of the other, and this one is our third condition. Two vectors are linearly dependent if and only if they are the multiple of, if one is the multiple of the other. You can also say that if they lie on the same line. Now look at the xyz plane. Say this one is our x-axis, this one is our y-axis, this one is our z-axis. So this plane is our xy plane, this one is our yz, this one is our xz plane. If three vectors are given only in this plane, or only in this plane, or only in this plane, then more than two vectors in these planes individually will not be independent. So in third case, any three vectors in R cube are linearly dependent if and only if they lie on the same plane. Also, from the linear combination of vectors we have x1 u1 plus x2 u2 plus x3 u3 plus x4 u4 up to xm um is equal to 0. Say these vectors u1, u2, um, u4 up to um, these are not linearly independent. Say these are dependent. And say u3 is our dependent vector. Say here this vector is our dependent vector. So move all these terms except this one on the right side, we will get x3 u3 is equal to minus x1 u1 minus x2 u2 minus x4 u4 up to minus xm um. Shift x3 on the other side means divide both sides by x3. We will get u3 is equal to minus x1 over x3 u1 minus x2 over x3 u2 minus x4 over x3 u4 up to minus xm over x3 um. Since x1, x2 up to xm all are scalars and their fraction also gives us a scalar, so let's say this one is our new scalar. So y u3 is equal to new scalar, say x1 star. Similarly, this one let's represent by x2 star. Say this one is our, since this vector is u4, so let's say this one is our x4 star up to xm star um star. So look at this new equation. This equation is basically a linear combination of u3 in terms of vectors u1, u2, u4 up to um. So this shows that if the vectors are linearly dependent, then you can write the dependent vectors in the linear combination of the other vectors. So these were the main points of linearly independent and dependent vectors. Hope so you will enjoy it. Feel free and ask questions in the comment section. Thank you.